Okay, good morning. Welcome to this tutorial, which is a part of a one-month program on multi-scale model simulation for quantum and kinetic problems. My name is Baowei Zhu from Department of Mathematics at NUS. So today it's my great pleasure to introduce Professor Eitan Tadmor, who is currently a distinguished university professor at the University of Maryland, College Park. He is an international leader in applied and computer mathematics. And Professor Tadmor is well known for his seminal contribution to the theory and computation of PDEs with diverse applications to shock waves, kinetic transport, in-compressed flows, image processing, and self-organized collector dynamics. He has numerous honors and awards. So he was an invited speaker to International Congress of Mathematicians in 2002. Some of you may be just born that year. And also he was elected American Mathematical Society Fellow in 2012, and also the SAM, Society of Industrial Applied Math Fellow 2021. And last year, he was elected a Fellow of European Academy of Sciences and Academia Europaea. And so was board on many journals. I don't want to spend too much time to touch, and also many named lectures. In addition, Eitan also a builder for institutes or networks. For example, he was founding co-director of the Eitan Institute for Pure and Applied Mathematics in UCLA, and also he is a coordinator of KNet and many others. So we are really honored and have Eitan to give a tutorial today and tomorrow, and also he will give a talk next week in workshop 1, and he will stay here for almost 2 weeks. And all of you are welcome to learn mathematics, learn how to establish a successful career in mathematics from him. He's really our role model in applied and computer mathematics. Eitan, yours.
Don't stop, just a second. Continue. Thank you very much, Riza. Okay, thank you all for coming. And I need to apologize if in the middle I have to cough, because I carried this cough for more than a month. So it's unpleasant, sorry. Okay, so I will give 4 lectures which are tied one way or the other to a multi-scale aspect in collective dynamics. And let me start. In the first lecture today, I will talk about something which I called emergence of multiflocks in collective dynamics. So I'll go slow because I'm not sure about the background of all of you. I try to stay with all of you, and please feel free to ask me questions. So first of all, about the formation of multiflocks. The multiscale aspect, there was a recent 2020, I think. 2020, so there was a recent issue in 2020 devoted to multiscale aspects in collective dynamics, and I really like the summary of them, which says that the multiscale methods in collective migration uncover new unifying organization principles and shed light on the transition from single to collective migration. This is really true in the sense that once you have multiscale aspect, you get a new kind of physics, or a new kind of dynamics, which you cannot inherit just by multiple single dynamics. That's what I will try to show you in this formation of multiflocks. And what I will do is I will try in this 1 hour to make a systematic derivation of the mathematics, not the biology, not the physics, of the formation of multiflocks, and I will try to convince you that it's generic. More often than not, you get multiflocks rather than one flock. And then if it's generic, it is important that we will learn what are the observable, what are the ingredients that define this kind of dynamics. Okay, so let me start. Before I talk about multiflocks, I have to spend some time to tell you about one flock. So this is what we are going to discuss. We are going to discuss agent-based description for alignment. So as you can see up at the top, what you have is a collection of agents, capital N of them, and each agent is identified by position and velocity. So the position is evolved according to the velocity, and the velocity, which is given in the second line, is given by a weighted sum of the different velocities. If we focus on agent number I, then we take a weighted sum of the differences between all the velocities Vj and Vi. And the statement behind it is that there is some sort of averaging that is going on there. So I will not elaborate now on this agent behavior and what does it entail. We will do it later on. But this will be the starting point because this is a phenomenological aspect of collective dynamics which is very important, which is different than attraction or repulsion. It's called alignment, and as we will go along, we will see what is the effect of alignment. The idea is that different agents try to align their velocities with the other agent through this process. Okay, what dictates the dynamics here is one thing which is not specified here, and this is the function phi. Phi is a symmetric function, I will assume, which depends on my position. Let's assume that I'm agent I, and the position of the other agent, agent J. So in some sense, this symmetric function, you can think of it as an influence function or communication function. It is the function, it's the kernel which defines the collectiveness of the dynamics, because it tells us how different agents communicate with other agents. And the only assumption that I will make here is that this kernel is positive. If it's zero, then there is no communication, and that it's symmetric. So the way I interact with my neighbors is symmetric. It's the same way that they interact with me. In most cases, it applies. In some cases, it does not. We make this assumption simply because it's simplifying the analysis. Now comes a very important assumption that is usually not discussed in the literature. In fact, most of this lecture is about topics which is not discussed in the literature. They put it aside. I'm bringing it to the mainstream. And the assumption is that the order of the interaction is of O of 1. So this means that the interaction is of O of 1. Let's take the case. I have to write certain things. That's a very good arrangement here. They told me to be here. So let's assume that this communication kernel is a function of the distance. This is just one example for a symmetric interaction. It's not the only example, but let's assume that we have now, so phi here is a function of two variables, and I abuse the notation. I take a function phi, which depends just on one variable, which is the distance, which is clearly symmetric. I will assume that the xi minus xj is greater than some number, which I will call the, I will assume that the distances are less equal than d. So this means that what we are discussing here is a collection of agents, and the distances, the diameter here is at most d. So you should think that there is a blob of agents. Of course, if the diameter d grows unboundedly, then there is no flock, there is no blob, there is nothing coherent that exists. So there will be an assumption here that the distances xi minus xj, the diameter of this crowd, is bounded from above. And if we assume also that phi is a decreasing function here, then this implies that phi of xi minus xj is bounded from below by phi of d. So you can see that the order of the interaction is at least O of 1. They all have this lower bound which is uniform to all the agents. So the first thing I would like to highlight is this assumption. This is the assumption that we have a flock. So this means that the distances are bounded from above. If the distances are bounded from above and phi is decreasing, it implies that the interactions are bounded from below. So this will be the assumption that all the interactions are of order O of 1. And then it means that when we look at the interactions, Vi equals the sum over J, phi of Xi, Xj, Vj minus Vi. When we look at this sum, it is of the order O of n, because each term here, this is O of 1, we assume that the relative velocities, they change in time. So they are O of 1, so we have here n terms, and everything on the right-hand side is of O of n. And then, what happens when this term is of O of n? It means that this dynamics, it peaks at time which is of the order 1 over n, which is precisely the reason that all the literature begins with rescaling here by a prefactor of 1 over n. So in fact, this kind of model goes after Cooker and Smale. They introduced this model in 2007, and they just started with 1 over n. And in fact, when you think about any model of interactions, there is always 1 over n in front of it. I don't know if you ask yourself the question, why 1 over n? Why 1 over n? There is no other reason. It's just scaling. In fact, there shouldn't be 1 over n. It should be just the sum of the forces. So the 1 over n is a scaling parameter. And the purpose of this 1 over n is in order to make the dynamics peak at time which is O of 1. By peak, I mean that's where the action is. The action, if we normalize by 1 over n, is a time which is O of 1. That's the only reason that we do it. Yes, Rizal.
This is 1 over n, because with this 1 over n, you can do mathematics. Otherwise, you cannot do anything.
Yes, but we pay for that dearly. And the talk is, what do we pay? So in fact, here's the question. What happens if these distances are not bounded by a d? What happens when these terms are not of the same order? Now, can it happen? When I will show you that generically it does happen, and when it does happen, this model does not work out. So you ask yourself a question, so how come it's not discussed in the literature? I don't know. I really do not know. Okay, but we have to dig inside a little bit here. So before we talk about multiflock, we have to discuss what happens to one flock. So give me now 4 slides to tell you what happens with one flock. What happens with one flock is the case, this is the good case, where all the terms here are O of 1, where the sum is O of n, when we normalize by 1 over n. This is the classical part of the literature. Let's see what happens as time goes on in this case. So this is essentially the scaling I was telling you about. We know that as Rizal said, the action now is O of 1, at time O of 1, and we ask ourselves what happens as n tends to infinity. We have a large crowd, or we ask what happens when t tends to infinity beyond 1 over n. It depends how you want to look at that. So we have to talk a little bit about that. Now I'm opening a new section. 4 slides, give me some leeway here because it's rather complicated. So the point is that we look at something which is called the empirical distribution. So the empirical distribution is defined in this manner, and the idea is very simple. Rather than seeing what happens to all the points and all the velocities, you should think that we look from above. We just look from above at this kind of collection of Dirac masses. And the reason that I now divide by n, this is just another normalization, but it has nothing to do with this problem. In fact, this 1 over n just in order to make this Dirac mass O of 1 when it acts on other function. It's a measure. In fact, I don't like this normalization, as you can see, so I can take a different point of view, and the point of view is that I write it as the sum of k runs from 1 to n, and then I'm writing mk delta x k of x, and then delta vk of v, where the mk is 1 over n. So I will pretend as if each agent has a mass, and they all have the same mass, 1 over n. So that the total mass, the total amount of weight is 1. So this is the case of uniform distribution. Okay? So we have here mass 1 over n. It's not just a scaling, and then the total mass is 1, and then everything is okay. And indeed, that's what I wrote here when I write this measure in terms of these masses. Now, what is this measure? So in the words of Villani, which I like, this measure observe the measurement, because you like to see how the positions and the velocities propagate in time. So rather than seeing the position and the velocities, you see them from above, and you can measure this by acting on other test functions, if you like. I'm sorry, I told you I'm sorry. And this measure, if we have the dynamics that is written up there, so the dynamics can be represented by, from above, by the so-called Liouville equation. Here's the Liouville equation. I will not write it on the board, but what you see here is a transport equation for this measure. So the transport has two parts. The first part, vi dotted with the gradient in x, is essentially the transition from x to the velocities. And the second part, which has to do with gradients of velocities and this communication kernel, this is the second part, as written up there. If you want to see that, the only thing you have to do is to test this function, this equation, Liouville equation, for the measures by any test function. If you test it with any test function, you will recover what is written on the top. So the Liouville equation is nothing but a, I wouldn't say fancy, but a correct way, compact way to write the agent-based description for the n independent agents. It's the only point that I don't like to put in my lecture, because I know that those who are not familiar, I'm losing them, but I hope that some of you have familiarity with kinetic theory. So this is the gate that we have to get into. And then there is one more thing that we need, and the one more thing is this assumption that the agents are indistinguishable. Namely, the pair of agent, which is agent 1, x1, v1, is completely identical to agent xn, vn. There is no preference between any one of these pairs. Okay, there is a long history of utilizing the kinetic formulation for this flocking dynamics. I cannot write all the names here, so from time to time I write at the bottom. So it started in 2008 in a joint work I had with Ha, and this was more phenomenological, and then over the years it became more and more formalized, and in particular Figali and Kang, and Natalini and Paul, and finally Schweitkoy in his book made it in a very formal way, justifying the passage from the agent-based description to the kinetic description. But once we have this kinetic description, if we take it for granted, we would like now to observe this measure. How do we observe this measure? We can observe it by taking what is called marginal distributions. So we probe it by taking any pair. Since all the pairs are the same, we will focus on pair number 1, x1 and v1, and then we will integrate all the other parameters, all the other pairs, which are denoted by x minus and v minus. And when we integrate, we get what I call mu n super 1. It depends only on x1 and v1. So this is called the marginal distribution, and it's how this pair interacts with the world. The rest is not interesting. So how this pair interacts with everything else. And since we integrate, so you can see that when we integrate the transport part, which has to do the gradient in space, when we integrate, we are left only with V1 times the grad x1. All the other terms will disappear. When we integrate the gradient with respect to velocity, well, now all these terms will disappear except the term with V1. So we will be left with the integral of the gradient with respect to V1 of the term phi of x1 and x2, right? Because everything else is not there. V2 minus V1, and then we get mu2, 2. What is mu2, 2? Well, now the agent, the pair, which is at x1 and v1, starts to interact with the pair 2, pair 3, pair 4, but the interaction with pair 2 and pair 3 is the same. Why? Because there is no difference between them. And therefore, when they interact with all these different pairs, we get n minus 1 times interactions, as if the first pair interacts with the second pair. And that's what is written in the line over there. So we get the interaction between pair 1 and pair 2. And you can see that the interaction consists of phi at x1 and x2. And then we get this second marginal, where we integrate the original measure mu_n with respect to x3 and v3 all the way to the other variables, but we still are left with the interaction between the pair 1 and pair 2. So this is the, I would say, the prototypical interaction between pairs, pair 1 and pair 2. And now the question is, what can we say about these second marginals? We started with the first marginal up there, and now we have the second marginal. So here comes an assumption which is hiding a long history and a lot of effort, mathematical and physical effort, which is the propagation of chaos. And I will just make a reference to the BBJKY hierarchy and the convergence of expectation in Schnitzman, but in fact, there is much more there. And the assumption simply says that the second marginals is a product of the first marginals in x1 and v1 and in x2 times v2. So this assumption that the second marginal is the product of the first two marginals is just an assumption, and there is no time and it's not the appropriate framework here to discuss it. We will just take it for granted. With this assumption, if we plug it into the previous line, so you can see x1 and v1, I call it x and v, and the second pair that it interacts from now on will be denoted by x prime and v prime. So this is a point of departure which is very important. For the rest of the talk, there will be only two pairs. The one pair that stays in xv, it's an arbitrary pair, of course. It was attributed to the first pair, but it's an arbitrary. And then there is another arbitrary pair positioned at x prime with velocity v prime. And it is the interaction which really matters. And according to Liouville equation, once we integrate and take into account the propagation of chaos, we end up with the following. If the first marginal, if the first marginal indeed converge to a function of x1, v1, and t, so this is an assumption, and the second marginal converge then to the product of these first marginals, then this function satisfies that its time derivative plus v dot grad xf, remember this is the term that you see up there, right? Because that's the only term that remains here. So this is the first term here. And then we get the gradient of v, right? This is the gradient of v here. The n minus 1 over n disappears to be 1. And then we get, of course, a bilinear interaction term. What is the bilinear interaction term? It's very simple. Here is the product of f at xv, and then f at, I'm sorry for this wrong notation, at x prime v prime at time t. So they interact. And the way they interact is, it depends really on the communication kernel which acts between the position x and x prime with the difference of velocities between v prime and v, and all of this is encoded here. And all this up there, you see the v2 minus v1 is actually borrowed from the original model. So the information of the interaction the interaction is really encoded in this quadratic term between f and f prime. Okay, so this is the Vlasov, this is the kinetic formulation. And what do we do with the kinetic formulation? For the kinetic formulation, we realize by taking its moments. So the idea is that we take this Vlasov equation, which is written here, and then we realize it by taking the moments. This is basically the last slide that I would like to mention about one flock. So we define the density by taking the average over all possible velocities, and then we define the momentum by taking the first moment of f over all possible velocities. Now, if you integrate the equation up there, the Vlasov equation, if you integrate with respect to v, you recover the mass equation. And if you integrate now you take now the first moment of this equation. So here's this equation, the Vlasov equation. We take the first moment, and now we have to integrate that. So the first term will clearly give us now the time derivative of the momentum. What do we do with this quadratic term, the second term here? The quadratic term, I wrote there, observe, this is the identity that v cross v can be written as the sum of these four terms, 1, 2, 3, 4. And when you integrate these first three terms, first three terms, what you get is rho times u cross u. So you get basically a macroscopic quantity. And finally, there is still a quadratic term that we do not know how to resolve, and we call it pressure. It's a tensor. With this notation, we end up with the following momentum equation. The momentum is balanced by the spatial derivative of rho u cross u plus a pressure. And on the right-hand side, when we integrate everything, we get essentially the alignment term, but now it's in a macroscopic terminology. Now, unfortunately, I know that this is a little bit too much to squeeze into one lecture because I want to talk about multiflocks. So you don't have to follow everything, but at least you get a roadmap. What is the story for the discussion in one flock? Okay. Yes. Sorry? Yes, because if you integrate the last equation with respect to x, then that's a good question, thank you. If you integrate the last equation with respect to x, the spatial derivative drops out, and if you look at the second term, which is the alignment, you integrate with respect to x, then by the antisymmetry, it vanishes.
Class, we have dt rho plus something equals 0. It's a granularity equation. Granularity equation. Ask Oleg now look at the equation.
Yes.
dt of rho, dt rho plus divergence rho u equals 0.
This is the first equation on the top. On the top there, on the top there, this is the mass equation. And of course, when you integrate, you get that the total mass is conserved. So let me I'll write it. So what you get here, and what you get in the momentum equation, well, let me write it simply like this. It will be simpler. Yeah.
Capital A term is dissipative or dispersive?
Neither. It's the alignment term. It's neither dissipative. It has the tendency that it wants the velocities to go in the same direction. So it does not exactly dissipate. It's different than repulsion and attraction. That's exactly the issue here. Okay, I apologize. I told you I cannot control it. Okay. So what about the pressure? I don't know anything about the pressure, to be honest. And therefore, most of the literature, almost all the literature, is devoted to the case when the pressure is 0. Lecture 3, I will develop a new theory for the pressure, and I will discuss that. For the time being, I will ignore the pressure. So let's see, let me summarize what we have done. So we went from an agent-based description, which is written here, and on top of that, you get this kind of kinetic model, and on top of that, you get this kind of macroscopic description. And here is a beautiful simulation, thanks to Sebastian Moch. Let's hope that it works out. Yeah. And I know that whenever I give this talk and people who are not familiar with kinetic formulation, they are not convinced what the hell is going on there with this measure. It's complicated. But when you see this, then you know that there is something there. Because what you see on the left is a different kind of agent-based description, but you can see the agents. And there are many agents, and you are not interested in the details. What you are really interested is in the observable on a larger scale. And what are the observable on the larger scales? You can see on the right-hand side, you get these kind of squares, and each square, depending on the color, tells you the concentration. And you see the difference of concentration on the left, and you can see the direction, the momentum, or the velocities. And the idea is that we are not interested in the detailed description which I started with. We are interested in the macroscopic observables on the right-hand side. These are the rho and the u that we formally derive. And the rho and the u capture the description in the agent-based, well, under certain assumption. I put here a lot under the rug. Okay. Do you have questions? Okay. Say it again. This flow is periodic. It's two-dimensional periodic. This is the. It's not the Cooker-Smale. It's the the Vickschek flow, which has other aspects which are stochastic. So I put it on the rug. I just bring this in order to visualize the process that before we went to this measure. Okay. Fine. So now that we know everything about one flock, now the discussion begins. And what I claim is that this one flock dynamics is sort of a rare situation. The canonical situation is when we have multiflock. Why multiflock? Well, let's take the case that our crowd, which is denoted by C, consists of two crowds, C1 and C2. And the point is that the two crowds are separated in space. So remember this crowd. Now suppose there's another crowd. So I will call this C1, this is C2, and let's assume that the size of C2 and the size of C1, they are relatively small relative to the distance between these two crowds. Of course, I have to quantify this. But initially, when you start with arbitrary collection of agents, they are not equidistributed. They can have some concentration initially, and another concentration, and this concentration could be separated. It's completely random. So let's see what is the effect when you have different concentration in space. This is where the discussion begins. Okay. So you see that suppose the distance is much larger than 1. So what happens if the distance is much larger than 1 and phi is decreasing, then the interaction between, you should think of these two crowds, their interaction is rather weak relative to the self-interaction inside this. And now, if the interaction is rather weak, you remember that we assume that all the interaction of the same order, but now they are not of the same order. So what will be the effect? So what will happen now is that you get now two crowds, and the statement will be now the following. You get crowd C1 and C2. Let's assume that the crowd C1 here is much larger than this crowd, it's completely random. What will be the effect? You remember that if you have a large crowd, then it peaks at a time which is 1 over the size of the crowd. So this means that the crowd C1 will peak. Peak means that the action will take place much earlier than the second crowd. So the large crowd will peak at time 1 over N1. The second crowd will peak at 1 over N2, which is much, much later. So basically what you get here now, you get 2 different clocks. The big crowd will act fast at time 1 over N1. The second crowd will act at time 1 over N2. So we have to have now 2 clocks. 1 clock is not enough. So what can we do? You see, if you divide by 1 over N, it will not work. Here's an example. Here's the large crowd. Here's the second crowd, C2. Suppose you divide by 1 over N. N is N1 plus N2. You see what happens from the point of view of the smaller crowd. Well, you divide by N1 plus N2. So N1 is so much bigger than N2 that it doesn't matter, because you see this term is much smaller than 1, and here you have only N2 terms, but you divide by 1 over N1, which is large. The whole right-hand side will be practically 0. And this brings me to the question, why do we divide by 1 over N? In fact, birds do not know how to count. We divide by 1 over N just because we want it to scale it. But the scaling is incorrect. If you divide by 1 over N, you essentially get the wrong clock. So the second crowd will stop. So how to fix it? So this is something that was worked out in 2011. And the idea is to introduce a different scaling, not 1 over N, but 1 over the degree. The degree is the sum of the phi ik. So I look at all the interaction between me, I'm agent I, and all my neighbors, and I sum these interactions. Now, what does it mean that we have this kind of degree? You can see it as follows. The degree for every agent here is essentially 1 over 4. Here it will be 1 over a large number, because the interaction between this agent and this agent is negligible. So in fact, when I take the degree here is, 10, and here it's 4. So it adapts itself to the size of the crowd. And this is the model that we introduced in 2011. And essentially, when we do this lambda I, which is 1 over the degree, or 1 over the sum of the interactions, it adapts itself to the size of the crowd. It ends up with something which is not symmetric, apropos this, but we will leave it aside. So this became very popular model because it's really a much more faithful description. But the truth of the matter, it is more faithful than the cuckoo-snail, but it's still not the final answer. Why? Well, you see, we have here different time scaling. This is satisfactory for crowd C1, it peaks at T1. Satisfactory for C2, it peaks later at T2, but it neglects taking into account the large effect of C1 on C2. We just treat one crowd, we treat another crowd, but when the smaller crowd comes into life, already the big crowd has an effect on it. We completely ignore that. And we ignore that because we don't have one clock, we don't know what to do. So this model fails to give the correct answer. And that's what I would like to do now. So I would like to use one clock for everything. I would like to come up with a master equation that takes into account the different scenarios. So now when we do this, we have to consider 3 scenarios. We have T1 and we have T2. T1 is when the big crowd gets into action. T2 is much later when the small crowds get into action. And then we get even beyond that. So let's see what happens before T1. Before T1, it's when the 2 crowds are still in the form of agents. They do not form really a continuum. And this is what is written here. We take this empirical measure for the first crowd, another empirical measure for the second crowd, and they just act as a collection of agents. And that's what's happening for T less than T1. You can see that the density, we have a density which is discrete. I take it as a discrete Dirac masses. And here's the momentum as a discrete Dirac masses in velocities. And you can see I sum it over alpha. So alpha is the index of the two crowds. Let's say alpha equal 1 and alpha equal 2. So we sum it. This is the rho u. And then when you write the equation, it doesn't matter if it's hydrodynamic or not because now it's discrete. What you get is exactly what I had before. What is written here is the usual Cooker-Smale that I had before, but with a twist. First of all, we normalize it by 1 over n beta. So n beta is the sum of the agents in crowd C beta. And you can see that each agent, which agent I in crowd alpha, interacts with all the other crowds. So in this case, it's only 1. And you can see that the interaction is correct. Here is my alpha I. It interacts with an agent J in crowd beta. Beta could be alpha, could be the other agents. And then this is the kind of interaction. And this captures basically the whole story. Okay, so this is for short time. Now we come to something which is much more interesting. What happens when T is greater than T1 and less than T2? What happens when T is greater than T1? When T is greater than T1, then C1, the large crowd, already is encoded in terms of hydrodynamic observables. Its density, 1, and its momentum. So the index 1 means belongs to the first crowd. But the second crowd still did not have enough time in order to form a flock. So it's still a discrete collection. And that's what is written there. And therefore now our density has a continuum part. This is crowd 1, and this is crowd 2. Crowd 1 and crowd 2. And now they interact. And when they interact, we get basically the hydrodynamics for crowd 1, with its pressure and everything else, which we saw before. And crowd 2, well, this is what's written for crowd 2. There is no pressure. In fact, the whole thing here is just a collection in crowd 2. It's just an agent-based description, a Cooker-Smale description. Okay, now how do we bring them together? That's the question. And the idea is, let's look at the crowd 1. So that's the first time I do this. Let's take the crowd 1 and let's look at its center of mass, x1, and center of momentum, v1. So we integrate this whole continuum over its support, and this is the first moment of the density, and the first moment, it's missing there. Yeah, there is a missing x because I want the center of momentum. Okay. Now, when I take this, I integrate the hydrodynamic equation, and I will get a term like that. So let me do it on the board because this is important enough. So I will do it here. So here is rho 1. Here is rho 1 u1. Here is the gradient rho 1 u1 cross u1. And here is the integral of phi x x prime, and then we get u prime u, and then we get rho prime, and then we integrate dx prime. Essentially, that's what's going on here. Now we have to take here u1 and rho 1, and that's basically what we are doing. Okay, now I take this equation, I take the first moment, and I integrate with just on the the support of crowd 1. So if I do this, I will get here the quantity in terms of the momentum of V1. This will disappear. And now I look at the interaction which is given here. That's what is written up there. So look at the interaction over there. I integrate. This is integrated on x prime. This is still another integral on S1. This is an integral of x prime on everything, S1 and S2. This is precisely what is written on the top. This is exactly what is written on the top. And now when you integrate on the top, you see I break the u prime into u1 prime and u2 prime. I break the rho prime into rho 1 prime and to rho 2 prime. And now I integrate on this kind of cross product. And when you do it correctly, all the terms disappear. This term drop out by antisymmetry, right? Look at the antisymmetry there. And the only thing that survives is this term. This is the only term that survives. So out of this whole hydrodynamics, you get the first term, which is the mass 1 times the average velocity v1 dot is given by this double integral. And that's what I would like to focus in. Because what happens here is that now you notice that ρ2 is discrete. So when I integrate dx prime, in fact, it's a sum, which I've written here in red terms. So this integration with respect to S2 is written, it turns into a summation on C2, and this is the x2j, and then I subtract here these terms, and that's exactly what's going on here. So of course, there are details here which are important, and multiflocking has to do with details. The important thing that I would like to emphasize is the following. Notice that the last line has the following aspect. We average on x, and we average on the second variable as well. So there are two separate averages here. There are two separate averages. We average on x, and we average on the other variable. The average on the other variable is using summation. The average on the x, you see that I integrate on x when it belongs to S1. And this is something that will persist throughout this description. The question is, what can I do with this integral? Okay, so now I make an assumption. I make the assumption that the integral here times ρ1 is roughly phi at x1 and x2. These are the center of masses times m1, and likewise for the momentum. So I'm making an assumption that this is an approximation. And with this, notice that actually it's not only that I average in x here, but in fact, you remember I also average in the second variable. These are in red here. So I have an average in each one of the variables. And then with this kind of assumed approximation, then we get phi at x and x prime. Of course, phi at x and x prime, x belongs to one crowd, x prime to another crowd. It's a small parameter, so it's a small number times some function of these two center of masses. And what we end up with is we just have one agent at x1 with velocity v1 interacting with v2. V2 is the rest of the crowd, which is the second crowd. So all of a sudden, this big blob, which stays here, there's a big blob here. But when you are here, you know what happens with this big blob. You see it just as a one point at the center of mass with the center of velocity. That's what happens. So these agents here, they just have one super agent, which is very heavy, far away. That's basically the moral of the story. And that's what we get here. So at the end, when t is between t1 and t2, what we get is that all these agents in the second crowd, they act like the usual agents. This is the usual interaction. And then they interact with the big agent, which is far away. So instead of having N1 agent, N2 agent, they have N2 plus 1 agent. So at the end, we started with agent, hydrodynamics, we got back into agent. And this is the summary of everything. And let me just summarize, we end up with a new agent-based dynamics, exactly what I said before, but there are two things which we have to pay attention. Now there's interaction between the agents, which we call phi, or phi 1,1, it's the interaction in crowd 1, but then there is another rule of interactions, which I call mu times psi, or phi 1,2, how this crowd interact with the one super agent here, so it's another kind of rule of interactions. Okay, since I don't have time, let's look at the long time dynamics. Now we have the long time dynamics when t is greater than t2. Now we have hydrodynamic description here, we have hydrodynamic description there, and here are the two hydrodynamic descriptions, and we integrate them. And when we integrate them, just as we had before, we get basically dynamics in terms of the center of mass and center of momentum, or the average velocity. And the dynamics looks like something exactly what we had before. And again, notice here, sorry, we have to integrate this interaction with respect to dx prime, and then we integrate everything with respect to dx. And in the, sort of the reflection of that is written here. So we always average in x and x prime. And we end up, lo and behold, with agent-based description for the center of mass. Now, I assume there are only two, but who said that there are many more than that? So in fact, we have center of mass indexed by alpha, x dot alpha is v alpha, and we have now masses alpha, velocities alpha, and what we get here is basically the usual system that we started with, right? Is exactly what we had here, but with a difference because now we have masses. Each blob has its own mass. So when we assumed at the beginning that all the masses are the same, this was a simplification that is unacceptable. We have to take into account that the masses here are different, right? We have different masses depending on the flock that we are talking about. So we are really approaching now the end, that at the end we get different masses and we get different communication kernels. Now we have to put all these things together. So we are left with 10 minutes. And the question, of course, before we put all these things together, everything I've done here was precise except one thing. I approximated the integrals. How do I know that this approximation of integral is correct? In what sense do we approximate the integrals? So this brings me to the last topic, which is separation of scales, and then I will summarize. So you remember, we take this kind of integral of rho 1, which is sort of like the mass rho 1 weighted of phi, and then we have the integral of rho 1 u1. Let's assume that phi decays it's like power of eta. So how do we know how to approximate that? So here's the idea. Take little x in S1, take little x prime in S2, and I want to approximate, of course, the distance between x and x prime to the power eta. So x minus x prime is written in this fashion, and then the idea is that the distance between x and x prime is essentially the distance between the corresponding centers of mass. That's basically the idea. Well, when I say essentially, what kind of error do we commit? So this is basically the computation that I'm doing here. When we take the difference between x minus x prime and we plug x minus x prime in terms of this is little r and this is capital R, the distance between the center of mass, you can see that this absolute value is given by the square root of r squared, little r squared, and cos theta, which is the angle between x and x prime and the other small locations. So basically, the picture that is missing here is we get one big blob, a small blob, here is the center of mass, here is this vector, and now here's a typical x prime, here is a little x prime, and we want to see what's going on here. So instead of seeing what's going on here, we look at this vector and then these little two vectors, and the point is that these little two vectors, their length is negligible relative to the distance between the centers of mass. So that's basically what is going on here. And indeed, if we make this expansion, we get an expansion in terms of Legendre polynomials. Would you believe? Did you know, I did not know that Legendre introduced Legendre polynomials for this reason, not for orthogonal polynomials. Legendre introduced Legendre polynomials in order to study the large time interactions in Newtonian potentials. Okay, so we follow that. We make this kind of expansion. I will spare you all the details, but the important thing here is that we get that this 1 over x minus x prime that we are interested is given here, and therefore when we take the eta power, which is basically the influence function, we get 1 over r to the power theta. This has to do with the center of mass, and then we get a linear term which is written here. And then we get a small term written over there. So let me write it again. So we integrate. So when we integrate, we get c over r eta. C over r eta is precisely phi, the interaction between the center of masses. Then we get a small error term, which is given here. And then finally, we get this middle term, which is written there. Let me slow down here because now this is important. This is basically the Legendre expansion. You see, x1 minus x, when you integrate dx rho 1, it drops out if you choose x1 to be the center of mass. This is the meaning of a center of mass. The integral of x1 minus x times rho 1x dx is 0. This means that capital X1 is the center of mass. And therefore, if you do that, you are left with a red term, and this red term is of this small order. It's still large relative to that, but it's still small. But more is true. I always average in the two directions. If now I take this red term and I further integrate with respect to, so if I further integrate with respect to x prime, which is written here, then even this term disappears if x2 is the center of mass. So de facto, the error that I get is not r over capital R, but r squared over capital R squared. It's much smaller. It's much smaller than we anticipated. And indeed, we get that this linear term interaction at the end is the interaction between the centers of mass times the product of the masses. Okay, so now we're basically concluding, except one thing. I just tell you about the mass. Now, what about the momentum? When you do the momentum, you got the center of momentum, and the center of momentum is not the center of mass. In fact, the center of momentum has to do with y, and y is now the first moment not of rho, but of rho times u. And you can see that this y and this x do not agree. So in fact, the whole thing seems to collapse, except that we have to know that in flocking, once we know that the diameter is bounded, the velocity average in the right direction, namely the velocity u alpha, really for large time approached its average, which is denoted by v alpha. So indeed, the x's and the y's, the centers of mass and momentum, coincide for large time, and everything else is justified. And the important thing is that the error that we commit here is of the order not epsilon, but epsilon squared. So in fact, the distance here need not be very large, and already you get this kind of analysis relevant. Already when the relative distances is like 1/5, you get a 2 orders of magnitude separation of scales. Okay, so what is the master equation? So in the paper that I had with Schweitkoy, we wrote a master equation in general, where you get interaction between agents, this is self-interactions, and cross-interactions with other crowds. So here's the self-interactions, here are the cross-interactions. You notice that there are masses here, and you notice that there are different kinds of communication kernels. And then, of course, if you integrate that, then you get back into the agent-based description I just told you. Okay. So let me summarize by saying that this interflocking behavior will be the topic of my next lecture. In the next lecture, I will really analyze this type of dynamics. And let me just say something like this, that the process here that we have done is the process of upscaling. We started with little x's and little velocities, and then we get densities and momentum. And then the densities and momentum got center of masses and velocities, that is centers of momentum. So we get this kind of super scaling, which is upscaling, coming from our master equations. Okay, so what is the conclusion? The conclusion is that multiflocks, the generation of multiflock the formation of multiflock is generic, because even if we have just a relative size which is not that small, already we get this kind of multiflocks, and we have to pay attention to the observables, and the observable are masses and different communication kernels. So we get not just one single communication kernels, by scale separation is different by different communication kernels. And then there is the role of flocking, which is very important, which I prepared it for this lecture. Actually, it was never been analyzed before. It is extremely important that we know that the dynamics is such that we approach the averages, and then it justified this kind of process. Okay, so I had to rush a little bit at the end in order to meet the time. Let me stop here, and if you have any questions, let me know. Thank you.
Thank you, Eitan, for very nice first part 1. I'm looking forward.
Okay. So, thank you.